Hello, everyone. Welcome to one more session of our Encora Global Dev Week 2023. I am Fabio Dassam. I am a software development manager here at Encora Brazil, and I'm very pleased to be your host in this session. Now we are going to talk about the alignment lens space, what it is, what is needed in the context of the generative AI, and some of the techniques and current developments in this field. Particular attention is given to alignment of large language models. Our speaker today is Jorge Diego Hernández Medina. Jorge Hernández has more than 2 decades of experience as a software engineer, with more than half spent in AI and machine learning space. He has led cross-functional distributed teams as both tech lead and CTO in delivering state-of-the-art results in data and text extraction using a novel machine learning algorithm developed in-house. He currently co-leads Encora's generative AI technical practices. I'd like to remind you that you can follow us in our social media networks appearing on the screen, so please do it, follow it to be aware of every news, okay? This session is part of the Global Dev Week organized by Encora. You can use the chat to leave comments and ask questions to the speaker. Jorge will be happy to answer all your questions using the chat, right? I'm excited about this talk, and I think most of you are too, so let me invite Jorge to lead this speech. Welcome, Jorge. The stage is all yours.
Thank you very much for that very nice presentation. If I don't know, bring up the slides. Thank you very much. So I'm going to be talking about the alignment landscape. And I'd like to start off by giving thanks and credit to all the people who've helped me form my ideas around this, in particular, Paul Cristiano and Victoria Kakovna from DeepMind, and Chris Ola from Anthropic, Return and Go from OpenAI. Lots of the stuff you will be hearing today is based on work they've done. The talk is divided into 3 parts. Basically, I'll give you an overview of the landscape and way of thinking about alignment. And then we'll dive into multiple different areas of research. And finally, I'll dive into what is my favorite area, which is mechanistic interpretability. So to start off, why alignment? So new AI systems, unlike previous systems, are far more general and resilient. Like, one of the characteristics and one of the big problems that AI used to have is that systems were very narrow. They could do only one thing. They could only, for example, play chess or move a particular robot for a particular task. And if you tried to do anything that was slightly different or out of the exact parameters that they've been trained on, they broke catastrophically. They couldn't deal with uncertainty. They couldn't deal with slight changes the way we humans do. But new models are different. In particular, large language models can do lots of things that we do with language. And that means that with scaling laws suggesting that basically we can just keep throwing compute at these models and they can keep scaling in capabilities. During the next decade, we can expect AI systems to become as good as humans in almost everything we do. And that means that AI has the potential to have huge positive impacts by helping accelerate research in science, medicine, technology, by making us far more productive, by making our jobs be more about how we can apply our creative abilities and not just do the rote memorization stuff that lots of jobs have, like as the day-to-day activities. Now, the bad thing about that is that we don't know how to design systems that are robustly helpful, honest, and harmless. Given the potential impact of AI systems and, of course, the rapid progress that I just mentioned, there's a risk that we run of actually deploying systems that are unsafe. And the ugly bit about that is that unlike previous technologies where, which had huge impact, like the printing press, like the internal combustion engine, like the internet itself, AI has the potential to act autonomously. What that means is that it can do stuff on its own. Like you can set it off, you can set an agent, or if it's an AGI, a sufficiently smart system, the kind of that we think can be developed in the future, it can get its own ideas and do whatever it wants. Now, that this could be catastrophic if the system isn't safe, either because the system pursues its own goals, which can be dangerous or inimical to humanity, or because we uh, overtrust the systems. That's one of the things that humans tend to do. We trust computer-generated stuff way too much, way more than we should. That's called automation bias. It's a problem. One of the problems that actually you see during the use of code generation tools. You actually have to train software engineers to read the software that's generated by these tools to not trust it as much as they normally would. Um, so if we give them too much trust, these things, even though they might have capabilities that exceed human ones, they still can make mistakes. And in high stakes situations, those mistakes can be really dangerous. So one way to think about alignment, about solving these issues, is what's called the alignment problem, which is the challenge of ensuring that AI systems actually pursue goals that match human values and not just what they want. And they similarly, and this is important, not just that they do what we wanted to do, but that they do not do stuff that we do not wish them to do. So one way of decomposing the problem, one way of thinking about the area, is one that comes from Victoria Kakovna, who's a researcher at Google DeepMind. And she thinks about the problem by dividing it into two halves. In the first half, you have what are called components. Components basically are the different elements of a system that we hope is aligned. Sorry. And on the other half, you have enablers, which are lines of research that make it easier to get those components right. And of course, this is just a way of thinking about it. It's not comprehensive. There are some topics that are sort of like a mix of both and don't fall easily into this taxonomy. And you can think of components in this particular way. We can talk about the different levels of specification. So basically, the specification is what the system what we want the system to do. So we write it out, we design it, and there are three levels there. There's the ideal specification, which represents our wishes about what the system will do. Then there's actually the design specification, which is what we actually implement in the system. A lot of the work of software engineers, as everyone knows, is actually making those two match. And then there's the rebuild specification, which is what does the system actually do in the end? Like what did it learn after training given the design specification? And the spaces between those two are where the alignment components appear. So there are two alignment components. The first one is outer alignment. And outer alignment happens when the design specification matches the ideal specification. That is, we designed the right objective. The main challenge for that is that human values are complex. They're context dependent, not explicitly known and well defined. Everyone has different values, different cultures hold different things at different levels of importance. And most of the time, if you start asking someone, hey, why do you do X? Why do you believe Y? They won't be able to explain it very well. We actually ourselves don't know where our values come from. We actually have entire fields of study for that. That's the whole point of ethics and aesthetics, to know why we think and believe in the stuff we do. And that makes, of course, making that match between ideal and design specifications hard. And then there's the second component, which appears between the design and the revealed specification. That's called inner alignment. And that happens, we have that when the revealed specification matches the design specification. That is, we correctly implemented the design objective, because you can design a good objective, but then whatever technique you use to train can actually not work. You can actually train it the wrong way, train the systems the wrong way. In particular, reinforcement learning models can develop what are called hidden objectives or treacherous turns, where they suddenly start doing stuff that you do not want them to do. So now I'll dive a little bit on the 4 of the enablers of alignment research. And starting off with specification, this is where work is performed to address rewarding specification. The current state of the art is something you probably heard about, which is reinforcement learning from human feedback. There's another talk being given by some of the people here that I suggest you listen to. It's a pretty big area. It's a complex algorithm. Actually, it's not that easy, but it can lead to what we call situationally aware reward hacking, which is basically that it, as everyone knows, there's this famous saying that if you use something as a metric, it will get gamed. And to avoid it, reinforcement learning from human feedback usually is used to train policies to assist human supervisor. We don't use it so much to train the model itself, but to assist the human training the model. And future lines of research beyond RLHF seek to implement protocols for supervising tasks that we ourselves are unable to directly evaluate. Because currently, reinforcement learning from human feedback depends wholly on being scored by humans. So on tasks where we don't do very well on that, we can't really currently apply it. And another line of research here under our specification is on the theoretical limitations of new protocols that are used to create the early AGIs, so that we can align them and use them to align more advanced AGIs. So we can actually use the AI systems to train the further generation of AI systems. Now, the second enabler I like to talk about is what's called goal misgeneralization. And even when you correctly specify the goals for an AI system, it can still learn unnecessary goals. One approach is to use what are called restrictor adversarial examples during training. You can think of it as the way GANs sort of work. The examples are designed to prompt and penalize misaligned behavior. So basically, you tempt the system to do bad things, and then you say, hey, no, that bad thing you just thought up, you shouldn't do that. Another approach, and this is one I'll dive deeper into later on in the talk, are what called interpretability techniques. Those techniques allow us to analyze the actual concepts being learned by the neural networks. And there are two main branches. One is mechanistic interpretability, which is looking at stuff from the bottom up, from the level of individual neurons to groups of neurons to layers and so on to the whole system. And then there's conceptual interpretability, which tries to do that from the human side, which is like try to understand the human interpretable concepts that the system is actually capturing and learning. And the next step, the next enabler that's really important is what are called agent foundations. And agent foundations work on the, you think, more theoretical level, because there are frameworks to bridge the gap between what we think of as idealized agents, like, for example, Jorge's AXI, which is, if you don't know about it, is an actual AGI. We actually have an algorithm for it. We actually know how to build a super intelligence. The problem is that that algorithm requires infinite amounts of compute. So it's not possible to build it in the real world. And real world agents, which probably will be embedded or embodied in realistic environments, since we actually want to deploy them and use them to solve problems all over. And there are three gaps which this line of research seeks to address. First of all, real world agents will act in environments which can contain copies of themselves or very similar agents. This is because you might want to have a robot doing some work, say, for example, in the field, picking fruit, and you're going to want not just one, you're going to want multiple of them, and you're going to want them to be able to work together. It turns out that decision theory, which is where a lot of the agent foundations work is done, or where it derives most of its foundations, no pun intended, from, actually says that the way that you work with people that are very similar, with agents that are very similar to yourself, if you're an agent, is different from the way that you work with agents that are different. And another problem is, of course, real world agents will interact with the physical implementations of the training process. That is, if you have a human that's training a model, the model can influence the human. And also, one of the big worries with AI is what are called as self-modifying agents. You can have an AI system that can modify its own code. Unlike us humans, we can't go and move our neurons around and teach ourselves stuff or change the way we behave just by thinking it. AI agents will be able to do all those kinds of things. So that's a big difference. And that gives them capabilities and ways of acting that can be dangerous if not controlled. And of course, they will face the same problem we face, which is that we are not certain about what the results of our beliefs and actions will be. Like, idealized agents have infinite time, infinite compute. They always know, they can always calculate the right thing. They go to the mathematical limit and they get the infinite sum of stuff. But in the real world, we just can't do that. And neither will our agents, our AI systems will be able to do that. So they have to be able to deal with uncertainty. And that's actually a really hard problem, because many of the characteristics that we would like the agents to have are not necessarily compatible with each other. So that's there's lots of work in decision theory about that. And that's some really fun mathematical stuff if you'd like to dive into it. And the final one is one that's not so mathematical. It's the other end of the spectrum, and that's AI governance. Understanding the political dynamics required for actors in the AI space to avoid an arms race during the pursuit to build and deploy AGI. This is hard as working on climate change, because it requires coordinating stuff from not just companies, but nation states and academia and NGOs. And there's work here in the creation of mechanisms to certify the characteristics of training runs and the capabilities of models. That is something that will need to happen. For example, the EU's AI Act is going to require people to record basically report a lot of the characteristics of the stuff that they're doing for really large language models, for example. And there's also work on proof of learning mechanisms for the training runs, tamper evident chip level logging, and on the design of actually test suits and benchmarks, so that we can actually determine what the capabilities and possible dangers of a system are. And finally, I like to talk about my favorite line of research here in alignment, which is mechanistic interpretability. Now, we say a model is mechanistically interpretable if we understand how it works inside, if we can comprehend its internal bits in terms of cause and effect and well understood principles. This includes understanding how the sequence of computations that are being done by the system actually end up solving the problem. What the role of the different components of the model, in this case, components are the layers, the different functions that we apply to the inputs and the outputs, and just how those inputs get transformed into outputs, and how that results in us being able to, in the model, being able to do a particular thing. It goes beyond predicting what the model will actually do, which is called predictive interpretability, and and understanding what the model's decisions are based on what the input and the output that it gets and generates, which is called input-output interpretability are. And it can be challenging. Current models are really complex. They have billions of parameters. Transformations there are nonlinear, so it's not that easy to understand at a human level what the math is actually doing, how the outputs are being modified, how the inputs are being modified. And of course, there's a trade-off between performance and interpretability. The more complex the model, the more powerful, but also the harder it is to understand. And one way of thinking about this is using what's called the reverse engineering perspective, and thinking about neural networks, thinking about the systems as a binary computer program that's being run on a really exotic virtual machine. So you have reverse engineering becomes mechanistic interpretability. Program binary becomes the network parameters. The VM processor or interpreter, the equivalent is the network architecture. The state or memory are the layer representations and the activations, and the variable memory and memory locations are the neurons and feature reactions. And one of the recent-ish work that's been done on that is done on vision circuits. In a very small model, I think it was only 10,000 parameters. They basically took the system that learned to detect cars, and they found neurons and groups of neurons where they could determine, hey, okay, so here is where it uses the fact that windows are usually on the top of the car, top part, and here's where it uses the fact that wheels are on the bottom part of the car. And it, sort of scores and adds all those three features: detect windows, detect car body, detect wheels, and if they're in the right order, then it learned. And they found basically these groups of neurons, this subgraph of the whole neural network that had the capacity to do these kind of things. And then they took that work, Anthropic, and took it further into LLMs. And they found that if you take transformers and you look at them at different layers, zero-layer transformer form what I call model bigram statistics. One-layer transformers ensemble those and with what are called skip trigrams, which are sequences of A, a skip, and B and C models. And two-layer transformers actually implement, using those foundations of the 0 and 1 layers, more complex algorithms using compositions of attention heads to create what they call induction heads. And those actually can do in-context learning. So actually, we can start to understand where the ability to do in-context learning for large language models comes from. This was done in a very small algorithm, so there's still lots of work to be done there to see if we can scale it up into more complex systems. And another use of mechanistic interpretability is to understand and predict phase transitions. Rapid phase transitions can be dangerous because we risk losing control of a system that suddenly becomes very, very good at something. An example of one is grokking, which is a sudden improvement in the test accuracy of a system long after it has achieved perfect accuracy in the training data. Like, it's perfect in the training data, but it can still improve on the actual test. And recent work on that found out that there are three different phases. First, it memorizes the data, then it forms circuits from the memorized features, and then it's sort of like when it learns to generalize, it takes those circuits learned and it replaces them with actually new circuits. So those are basically some of the lines of research in alignment. This is an important area, and there's tons of work in it. And thank you for listening to me. Hope you enjoyed the talk.
It was really a great session. We are very grateful for you, for all the shared knowledge today. Thank you very much. It was incredible. Also, thank you folks for all the messages and comments on the chat. I hope you have enjoyed this session, this presentation. Don't forget to take a look at the official agenda on our website to discover other interesting things and topics and presentations. Hope to see you all in the next session. Thank you very much. Thank you, Jorge. Bye-bye, guys. See you.
Bye-bye.